first video in the solutions chapter. This is 13.4, colligative properties of matter. So to effectively learn this lesson, please make sure you guys have printed out your companion worksheet. You're going to need to have your C-cert and open it up to a periodic table. You will need a calculator, and of course, you will need your notes. So without any further ado, let's get started. So I bet you guys are wondering what a colligative property actually is. Well, simply put, the colligative property is any property of matter that is affected and changed by the addition of a non-volatile solute. Non-volatile meaning something that will not evaporate easily. And you'll notice on the right-hand side of the screen, we are watching sodium chloride dissolve in water. So the solute here is sodium chloride. Believe it or not, because we are now dissolving sodium chloride in what was once a pure solvent, which is just water molecules, imagine this water would not have a boiling point of 100 degrees. The addition of that solute would change its boiling point. So the property of boiling would be altered. Or imagine it not freezing at 0. That would get altered as well. So colligative properties are actually pretty cool, and we can leverage them sometimes to achieve different means to an end, and we'll go into that a little bit later. One of the things that you need to understand is that how much the property changes does not depend on the nature of the particle or its identity, meaning that, like, for instance, if something was ionic versus covalent, it really wouldn't make a difference. And the example you give here is, equal amounts of KCl and NaCl are going to alter the boiling point of water to the same extent. So these colligative properties change based on just the sheer number of how many particles get added. Doesn't matter what they are or what class of compound they fall into. It's just how many actually get dissolved. I'm going to bring a special guest in. Of course, you guys see here, it is Professor Dave. He knows a lot about the sciences. So he's going to talk through colligative properties of boiling point, freezing point, and vapor pressure. And you guys are going to want to jot down some of what he has to say on your companion worksheet. So click the video, get your companion worksheet ready, and when you're ready to go, here's Professor Dave.
He knows a lot about the science stuff. Professor Dave explains.
A solution will behave differently from a pure solvent because there are particles of solute that interfere with physical processes like phase changes. A solution will display certain colligative properties that depend only on the concentration of solute and not on the chemical identity of the solute particles. Adding solute to a solvent will change things in the following ways: vapor pressure lowering, boiling point elevation, and freezing point depression. When we look at colligative properties, the key theme is that the presence of solute particles interferes with the activity of solvent particles at the interface between two phases. A liquid will always have a particular vapor pressure since particles at the surface of the liquid can spontaneously enter the gas phase. The number of gaseous particles determines the vapor pressure. But solute particles sitting at the interface occupy some of the surface area, which hinders some solvent molecules from evaporating. Therefore, the presence of the solute causes the vapor pressure of the liquid to decrease. A similar phenomenon is that of boiling point elevation. When a solution is raised to the temperature at which the solvent should boil, again, there are solute particles blocking the solvent molecules from going into the gas phase. This means more heat energy will be needed to compensate for this activity, which results in an elevated boiling point. The more solute there is, the more dramatic the effect. Freezing point depression is similar, but deals with the interface between the liquid and solid phases. For a liquid to freeze, it has to form a lattice. The presence of solute particles interferes with the ability of the solvent particles to efficiently form the lattice. So to compensate, the system will have to reach an even lower temperature to freeze. This is why we add salt to icy streets, because it causes the water to freeze at a lower temperature, so water will remain liquid instead of turning to ice until lower temperatures are reached, thus reducing the quantity of ice that will form.
Let's offer up a huge shout out to Professor Dave for joining us in our flip video. We look forward to more segments from more guest stars. Professor Dave, thanks for stopping by. So what I really want to get into now is just a summary of some of the things that Professor Dave talked about, and begin by talking about the boiling point elevation. Hopefully you guys pulled from the video that the addition of a soluble solute to a solution increases the solution's boiling point. So that's the cause. Why that happens can be seen here at the interface layer, where all these solvent particles are trying to evaporate. You will notice that the solute is sitting here and effectively interfering with the pathway to go reach the vapor phase. So it is important to understand that why does a boiling point go up? Well, a solution actually needs more kinetic energy in order for the particles to steamroll through these particles that are here that are blocking its pathway. So in effect, the boiling point actually goes up. Maybe where average kinetic energy, let's say, of 100 degrees Celsius was enough for pure water to boil, once we have those hydrated ions that are in solution, maybe it needs 101, 103, 100.5 degrees in order to enter the vapor phase. This is an animation that actually illustrates this concept. You guys can see that here is a pure solvent, and you can notice that particles are having no trouble reaching the vapor phase, whereas in a case like this, at the same temperature, because there are now ions that are in here, the ions are obstructing certain particles from actually entering the vapor phase, and in order for these solvent particles to actually become a gas, they would have to move faster. The best analogy I can give for boiling point elevation is if you all will think back to playing the mighty playground game of Red Rover when you were back in elementary school. Check this out and see if you can piece together what I mean by that by watching this short video.
Red Rover, send Sarah right over. All right.
Here she goes. Here she goes. Oh no.
Hold on tight, hold on tight. She worked. All right. Yeah, you're on the little too now. Red Rover, send Allie right over. Get up.
Ready to go.
Get it.
I can pick one?
Yeah.
Choose me.
This is sorry, guys. Sorry.
Guys, this is going great. You got all the dance.
That was awesome. Everybody loves Red Rover. So I guess the connection with Red Rover is essentially if those solvent particles on the right did want to enter the gas phase, they would have to be a little bit like Allie, where they would have to be moving with greater average kinetic energy and hit those particles with enough force so that they can get through them and enter the vapor phase. When we see an increase in average kinetic energy, we see an increase in temperature, and thus the addition of that solute made the boiling point higher and elevated it. Moving on to freezing point depression, let's summarize a little bit about what Professor Dave said. He brought up the point about salting the roads in the winter. Now, why do we want to do that? Well, we don't want water that is on the roads or slush to actually freeze. The addition of salt provided by the salt truck here in the city of Knoxville causes the slush or the water that's on the road to freeze at a lower temperature. When that salt is actually dissolved, it's actually going to cause a problem with intermolecular force formation. Check this out. What winds up happening is, you guys know, when you want to form an intermolecular force, your particles need to be oriented correctly. And when we add in a nonvolatile solute like the salt that's here, the salt can get between the solvent particles. What that winds up doing is interfering with that formation of the intermolecular forces. And in order for any intermolecular forces to actually form, the particles need to be moving considerably slower. So that causes the formation of ice to happen at a much lower temperature. So instead of maybe freezing at 0 degrees Celsius, we're going to add a whole bunch of salt to the roads, and once that is dissolved by any water that's on it, maybe the roads will freeze at -10, -8, -11, which is far better than freezing at 0 degrees. Our last colligative property is vapor pressure, and what I want to do now is just talk through the changes that are happening on a particle level that is causing the vapor pressure to be depressed when you dissolve solute in solvent. If we look at this animation, the first thing we're going to see is, yes, the aqueous sugar solution and the water solution are both evaporating, but it is clear that the water solution is evaporating faster. The aqueous sugar solution is not evaporating as fast and is not producing as many particles into the vapor phase. So one of the things that we can understand is that if we don't see a lot of particles entering the vapor phase, there are not a lot of particles colliding with the walls of a container or anything, and therefore we have a depressed vapor pressure. So as we look at cause and effect, the reduced number of collisions that are caused by fewer particles entering the vapor phase reduces our vapor pressure. Here we have the Dead Sea, and what's interesting about this is everybody's always so worried about the Dead Sea evaporating. Well, yes, it is evaporating, but because of these colligative properties, as more and more water actually evaporates out of the Dead Sea, the greater the concentration of dissolved salts and minerals will be, and that's actually going to cause the evaporation rate to slow. That's great news for everybody who wants Dead Sea salts and scrub and everything if you are looking to exfoliate with a natural method. So quick quiz for you guys. Which one of these substances would raise the boiling point of 1 liter of water more? Would it be an equal number of moles of NaCl, Cacl, or glucose that's here? The answer actually is the one that has the highest Van Hoff number, which in this case is the calcium chloride. When calcium chloride dissociates in solution, it is going to break up into 3 pieces. Sodium chloride only broke up into 2, and of course, as we know, something like glucose, which is covalent, only breaks up into 1. So, do not be that guy. So that's about it for our qualitative video on colligative properties. Make sure if you had any questions that you bring them with you to class tomorrow when we discuss things during the burning questions segment. And picking up after this video, we will also look forward to calculating the quantitative changes associated with colligative properties. Be on the lookout for that video as well. So till then, peace out!
That's all, folks.